Hi everybody, I'm going to continue my combustion tutorial. Right now it's going to be a steady state Fluent simulation. First thing is I made the geometry using SolidWorks. I have another video up on my channel that you can watch if you want to know, but basically I made the fluid domain, and what I'm going to do right now is import it into Workbench. So this is my part. You can also browse and find the correct part. I'm going to open up the geometry to make sure everything's correct. If any of you have seen my other combustion tutorial that I recently took down, then I'm sorry, but basically what happened is I was not pleased with the quality of that recording, so I'm redoing it right now. Basically you want to make sure in the geometry that your fluid domain is in fact listed as a fluid. Currently it's set as a solid, so let's go ahead and switch it over to fluid. Okay, now we can close this and we can edit the mesh. In meshing, I'm going to name the inlet for the fuel injectors, the air injectors, and the primary air, and then I'm also going to name the outlet. And as far as the mesh goes, I'm going to set an element size, but I'm not going to do any sizing of any kind other than that. Meshing in itself is its own subject, so it's not really the purpose of this video to go too much into it, but basically for naming the inlets, what you want to do is make sure that you have the face chosen. Go ahead and click whichever face you are trying to select and hold Control down and continue. These are our fuel injector inlets. Right click on the surface and create name selection. This will be useful later on in the solver when you're setting up the boundary condition. These are going to be our air inlets, air injectors. I would rather call it secondary air. And then this right here is our primary air inlet. Okay, now let's go ahead and name the outlet. Right click, create name selection. Alright, let's just go ahead and check we've got all those set up. Let's go into isometric view. Alright, now as far as the mesh goes, again, I'm going to keep it simple. You want to spend as much time as possible on refining your mesh, but I am not going to do that right now. Alright, let's see what that gives us. This might take some time, so I'm gonna come back when this is ready. Okay, so our mesh has been created. Next thing I'm gonna do is go into the setup. Make sure this is updated. Now I'm gonna edit the setup. Okay, under models, you want to turn the energy equation on. We're going to do K epsilon. For radiation, we're going to use P1 model. And species, we're going to do non-premixed combustion. Okay. Now under here it's important that we do the following. You have to create a PDF table. So you want to make sure that for what I'm going to be showing you, I'm going to use the mass fraction. So if this is mole fraction selected and you do what I'm telling you, then you'll get the wrong results. You can use either one, but you're going to have to put in the correct numbers into here and later on as well. So I'm using the mass fraction. We're going to use methane. I'm going to put 1. Okay. And then you can also select the temperature for the fuel and oxygen. I'm not going to change any of that right now. And then click Calculate PDF Table. Still thinking. Okay, finish thinking. Click OK. Now the first thing you need to do is go to File, Export PDF. And I've done this case before. I'm just going to save it in the same place. Okay, now we haven't saved the project yet. We should do that. Combustor tutorial 2. Okay. Next thing is we want to go into boundary conditions, fuel injectors, change it to a mass flow inlet. And this is actually where I need to do a little bit of speaking to you about what would be the stoichiometric equations and the stoichiometric ratio, the equivalency ratio, in order to determine the correct amount of fuel and air that you put into the combustor. The thing is that there's a website I want to recommend that you go and see, and there's a very, very thorough presentation that you can watch. And here it is down here. If you just Google eSurfax, okay, go to their actually let's do eSurfax Combustion or e-learning. That's the website, eSurfax e-learning. Okay, and then go to combustion, and let me see, which one is it? It's one of these here. I believe it's this one here. Conservation equations for, oh no, that's wrong. It's computation of adiabatic flame temperature. You need to go into here. And if you watch even just the first half of this lecture, you'll know everything you need to know in order to select the correct fuel to air mixtures in your combustor. Okay? Now, for me, I have a very, very short MATLAB program here that you can pause and look at if you want. But what I've done here is I did the stoichiometric equations by hand, and given that the equivalency ratio is 1, then in other words, you don't have an excess of air to your fuel. The percentage of methane I've assumed to be 5.5%. Okay, so if I have a room, or a room full of air which consists of nitrogen and oxygen, if I put 5.5% of that volume to be methane, it would be the perfect time, as you'll see in the lecture, the professor says, is the perfect time to light a match. So this very short MATLAB program, what it does is I use the lower heating value of methane, and I want 35 kilowatts of power. This is the number of fuel injectors, number of air injectors. So what first thing I do is I find the fuel mass flow rate over the entire combustor to be the power divided by the lower heating value. Then from there I find the mass flow rate for an individual injector by dividing the total mass flow rate in the fuel by the number of fuel injectors. Then down here, m dot air total, so the total air flow flowing through the combustor. This is just a conversion to make sure that only 5.5% of the volume is fuel. Then here I go m dot prime air. So if you remember, I have a primary air inlet, and then I have a the secondary, or the fuel injectors. So here what I'm doing is I'm saying that I want 75% of my total air to go into my primary air inlet. That might change, or that will definitely change on any of your designs. It depends on your design, depends on your combustor, right? So I've got 75% going to my primary air, and then the rest of it, 25%, I divide by the number of air injectors, and that gives me the m dot of the air injectors. Okay, so simple as that. When I run that, it gives me these results right here, and we're going to enter these into Fluent right now. So for the fuel injectors, let me just check, go back to the MATLAB code. So m dot fuel total, m dot fuel injectors, I have 1.1667 e to the negative 4. Okay, enter that. I'm going to choose normal to boundary for the direction. I'm going to choose intensity and viscosity ratio. I'm going to keep the temperature the same, although very often it will be, up to 900 Kelvin. And for the fuel injectors, anywhere you have species coming in through a face, you need to make sure that the mean mixture fraction is set to 1. Okay, and that's it for the fuel injectors. Outlet, leave it as a pressure outlet. Primary air needs to be a mass flow inlet. And let's go ahead and check actually really quickly what the primary air mass flow is going to be. Primary air is 0.0095 kilograms per second. normal to boundary. And here, because there's no fuel, leave the mean mixture fraction as 0. Secondary air, let's just check really quickly what our flow rate is going to be for the secondary air, or the fuel injectors. It's going to be 7.9545 e to the negative. So as I was saying, the fuel mass flow rate, we already did. We did the primary mass flow rate. Now we're going to do the injectors for the air, secondary injectors. It's 7.9545 e to the negative 4 kilograms per second. I got a phone call. Okay, so sorry about that. So we have the flow rate for the secondary air. Choose this normal to boundary. Species 0, okay. Now, what I'm going to do is I'm going to go ahead and initialize and run the calculation. If you run, the calculation and you have problems with the residuals, you're going to have to come back to these under relaxation factors, and most likely you're going to have to change something with the P1 or the energy or the temperature. Something might have to drop a little bit, but you always want to run it the first time without changing any of the defaults. So let's go ahead and initialize. Okay, and I'm just going to run a small number of iterations because I'm going to cancel them. I'm going to interrupt the solution right now for the purpose of this video. But realistically, that number should be like 2,000, okay, if you have the time to wait out the solution. Okay, so let's click calculate. I'm just going to let it run for a couple of iterations so that I can show you at least a taste of what the results will be if you wait it out. Okay, I think I'm going to come back in a couple minutes. Just I'm going to pause it until this iterations go a little further. Okay, so our 30 iterations are done. I came up with some errors, but again, it really comes down to I have to probably change some of the under relaxation factors in the solution control section. But everybody's case is going to be slightly different, and you might have to do different things to solve your problems. But this is really, the errors are something that comes up given a certain situation, and you have to find different types of solutions to those problems. But what I'm going to do is go ahead and show you, even though we got some errors, even though we had only 30 iterations, I'll still show you what we got within those 30 iterations. So I'm going to show you the temperature, and I'm going to create some new planes, pointed and normal, one in the X, one in the Z, and one in the Y. The Y, I believe I have to make this 0. Okay. Alright, so So let's go ahead and choose those planes that we just made and display them. And there you go. We have some, looks like we have some combustion happening. Looks pretty nice. And this is just a simple, ultra simple combustor geometry, but when you get into like cooling ducts coming in through the sides, when you have vanes, when you have swirlers, it gets much more interesting. But you know, given the tools, given what I've shown you here, sorry, 1 second. Given the tools that I've shown you here, you can do much more than you know, many more types of simulations with combustion. So if we look at this, these are the temperature contours, right? So you've got the highest temperature points here. Let's go ahead and look at some other things. Let's look at the species. It's a good idea to have a look at the mass fraction of different species. So the mass fraction of methane. So this is good. This is what we kind of expect with this. We have a high mass fraction of fuel coming in through the fuel injectors, and then immediately it's dissipating or being burnt. It's converting into different species. So if we were to look at this, we can also look at the mass fraction of let me see, OH right here. OH is usually a good indicator of the flame front. So if you see, looks like our flame front is located there. Okay, and then we can do mass fraction of oxygen. That looks pretty neat. You've got a good amount of air coming in through the primary air and the secondary air. And for those of you that watched my other combustion tutorial, which I recently took down, and this is replacing that, you'll notice the big difference between these contours versus what we had before, where before I had a lean mixture. I had not enough fuel in the combustion. I'm sorry, no, it was rich. Forgive me. It was rich, and I had too much fuel for the amount of air. And I went back and I've corrected those numbers now in this tutorial. And this is what you should see. This is with 5.5% of methane in the combustion chamber. It's being burnt completely, whereas before we had, if you recall, we had oxygen coming in through the inlets, but then it was being used up completely right as it entered the chamber, and there wasn't enough air for the amount of fuel. A lot of times you'll even have an excess amount of air for your fuel, even 10-15%. That depends on the combustor, depends on what you want to achieve. You can do things like lower the NOx, you can lower the CO2 by manipulating those numbers, and of course the design of the combustor. So anyways, this is just a a short tutorial for you people out there that might be interested in doing similar simulations with combustion. I hope this helped. If you liked it, let me know. Like the video, leave me a comment. If you'd like some other tutorials, let me know. I'm going to be starting my fall semester this upcoming week, so unfortunately I made like several videos this summer, but I'm going to have to probably slow it down a little bit. But still, let me know if there's some interesting projects out there. Something that can be done within 35 minutes, because no one wants to watch for 45 minutes or for an hour and a half. So, thank you very much for watching, and I hope this helps someone, and I hope you enjoyed it. Thanks. So long.